Ladies and gentlemen, welcome to the CIL eAcademy and today's guest lecture by Professor Benjamin Horton on mapping sea level rise in time, space, and probability. This event is scheduled to run for approximately 60 minutes. I'll now hand you over to the co-director of the eAcademy, Professor Patricia Galvao-Teles.
Thank you so much, Zoe. Greetings to all and very warm welcome to Professor Benjamin Horton. It's really a pleasure to have you with us. Today we have, this week, it's our module on climate change, and we had an excellent lecture yesterday with Professor Christina Voigt, and she will continue tomorrow. But today we thought we would have for our guest lecture, our Wednesday guest lecture, rather than a lawyer, which we've had for every model, we would have a scientist to explain us a bit more about climate change. Since science is so important for understanding and also for knowing how to fight climate change. So Professor Benjamin Horton is director of the Earth Observatory of Singapore at the Nanyang Technological University. He has been a professor also at Rutgers University and at the University of Pennsylvania after having obtained a PhD in earth sciences at the University of Durham in the UK. I'm not going to read out all this CV because I know we have to finish promptly at 5 o'clock, but I just wanted to highlight that Professor Horton has been an author of the IPCC Fifth Assessment Report, and he's a review editor for the new Sixth Assessment Report. And on his CV, I found an interesting line saying that his work, his research has been cited by President Obama in his 2015 State of the Union address at the United States Capitol in January 20th, 2015. He has published many articles, including in such high-profile periodicals as Science and Nature. And his research concerns mainly sea level change, and that's why he has chosen to speak to us about mapping sea level change. So we're really happy to have you with us, and we welcome your presence and your availability also to answer some questions at the end of your presentation. I'm sure that the participants will have some questions for you, so we'll leave some time for that. And I'm very happy to pass the floor to you. Very warm welcome to you, Professor Horton.
Good afternoon, everyone. So I'm going to now try and share my screen. All right, well, thank you for that introduction. My name's Professor Ben Horton. I am director of the Earth Observatory of Singapore. So I don't know how many people here have heard of this observatory. It's been in existence for around 12 years. It's known as a research centre of excellence. And there's only 5 of these here in Singapore. We employ approximately 150 scientists. We study topics of geohazards, earthquakes, tsunamis, volcanoes, and also climate change. We have a centre of geohazard observations here at the Earth Observatory of Singapore, where we have 175 stations around Southeast Asia, which are giving us in real time climate-related information. As Patricia said, I am a sea level scientist. I've been studying sea level for over 25 years. I got my PhD in earth science. So I was very much interested in how sea level of the past related to changes in the earth and in climate. I wasn't particularly that concerned about projections of sea level. But as my career has progressed, I found what I was doing was policy relevant science. And as was highlighted, President Obama cited me in his State of the Union address. So a president gives an address once a year, And in 2015, President Obama spent some time talking about climate change. And in that year, I'd published a paper in the Proceedings of the National Academy of Sciences, which showed that the rates of sea level rise in the 20th century were faster than anything that had occurred over the previous 2,000 years. So it's a very strong argument to say that we're living in unusual times if you can show that the rates of change in any climate variable is unprecedented. We showed it was the last 2,000 years, and President Obama used it in his State of the Union address. We then went on a year later to extend our record and said it was the fastest in 3,000 years, and President Obama tweeted that out. I've had no such recognition from the current president of the United States, neither would I expect such information, as he would classify what I do as fake news. But maybe, hopefully, next Tuesday, Trump will be removed. And there are many, many reasons to remove Donald Trump from power to do with his corruption. But one of the most important is on climate change. I do not think we can solve the climate emergency without the US remaining in the Paris Agreement. President Trump will he will sign the declaration removing the United States on the 4th of November if he's still in power. If he is removed from power and Biden is in there, then they stay in the Paris Agreement. If the US stays in the Paris Agreement, that means that the three largest polluters, the US, the European Union, and China, have all committed to solving the climate problem. Without the US, it will fall apart. So next week's election is huge. And I spent 15 years of my life living in the United States. I interestingly signed for my job in Singapore on the night President Trump won that election. I was very undecided. I had a great job in the United States, very undecided to come to Singapore. And when Trump won Florida, I went and I signed and sent my PDF off. Anyhow, that's a backstory. What I want to do today, I want to talk to you about sea level change. And I'm going to go through some very simplistic topics, but I'm also going to go through some quite complex products. And for a group of lawyers, I think some of it you'll get and some of it will be new to you. And it's based around the publication that you can see in front of you. This publication, it came out in 2018. I wrote it together with my team here at EOS, and I wrote it to form sort of like a lit review because it's an annual review, so I had a lit review on the state of science and sea level rise that then could feed into the next IPCC report. So it was mentioned I was an author on the 5th assessment report. We're currently doing the 6th assessment report. I'm an editor on that. It will come out sometime in the pandemic's delayed things, but I still think it will come out sometime towards the end of 2021, early 2022. The IPCC is a United Nations governmental organization. They meet and review and produce products all the time, but we have these main reports. They come out every 6 to 7 years. There are 3 of them. There's the physical science basis, there's adaptation, and then there's mitigation. I'm on the physical science basis. I'm the only Singaporean scientist on the IPCC. Compared to other nations, particularly developed nations, Singapore's a bit behind the 8 ball on this. They don't have much depth in climate science. I'm one of the few scientists in this country that does that. Anyhow, so let's begin. The other thing I would say is if you have any questions, I'm quite prepared to answer them as I go along, or we can do a bit of a Q&A when I finish. So this presentation, I'm basically going to try and go through 4 aspects here. They're all based upon recent research that we've done at the Earth Observatory of Singapore. The first thing I want to try and explain to you is that sea level is very, very complex, and it varies from different locations based upon the processes that are dominant at any individual location. Well, then I want to look back through time. I want to look at what's been happening to sea level over the last 10,000 years. That's the Holocene time period. This is the time period where the Earth warmed up from the last glacial maximum, sea levels rose, and the understanding of how sea level changed in the past provides a context for understanding the instrumental record of the 20th century and also the 21st century. 20th century dominated by instrumental measurements from tide gauges. 21st century, we now have satellite-based informations. We can then use that information to look at impacts. And one of the things that I've been looking at, based here in Southeast Asia, is looking at the impacts on our mangroves along our coastlines. And then I'm going to try and spend a little bit of time thinking about the future. So what do we know about projections of the future? And I'll provide some estimations from the modeling work that we've done for Singapore, Manila, Sweden, and New York City. So first of all, sea level is complex, and sea level is complex because there are a variety of mechanisms that dominate sea level at the global, regional, or local scale. At the global scale, it's processes that control ocean volume. If you increase the ocean temperatures, the ocean volume increases and hence sea level rises. The second process at the global scale is a mass problem. So if you have an increase in atmosphere and ocean temperatures, it melts our land-based ice and causes sea level to rise. And we have huge quantities of land-based ice on our planet. Greenland, for example, Greenland has enough water within it that if all of Greenland was to melt, it would raise global sea levels by about 6 meters. But it is Antarctica that the scientific community is very worried about. Antarctica has a colossal 65 meters of sea level equivalent within it. So you only need to melt a minor percentage of that ice sheet to have devastating effects around the globe. But sea level will be greater or less than the global average because of regional processes. So here in Southeast Asia, we have to, if we're going to look at sea level rise, we have to know what's happening with our ocean processes, ocean circulations. We have to know what's happening with the land because sea level is a combination of land and ocean. And so here in Southeast Asia, we have tectonic activity, and we need to understand whether we're having land uplift or land subsidence both between or during earthquakes, which can cause significant differences in coastal inundation. And then on the local scale, we need to understand on our deltas, sediment compaction, huge sediment loads coming into deltas. They weigh down the Earth's surface and cause it to subside. That's why Bangkok has a lot of problems with sea level rise. And we also need to understand groundwater extraction. Groundwater extraction causes subsidence. In Jakarta, land is subsiding at some 12 centimeters per year because water is being extracted for agricultural, industrial, and commercial uses. Now, all of these processes are not uniform in time or in space. So this graphic that comes from the publication I introduced my talk looks at a variety of different processes and says what time duration that they operate in, from seconds through to hundreds of thousands of years, and what the potential magnitude is by their color scaling. So ocean dynamics. So ocean dynamics relates to atmosphere-ocean interactions. That influences sea level on the order of from seconds to minutes to days, over through to centuries, and its magnitude is somewhere in the order of between around 10 centimeters and a few meters. At the other end of the spectrum, we have dynamic topography. Dynamic topography is changes in the Earth's circulatory cells in the Earth's core, causing changes in land heights. That influences sea level on timescales of tens of thousands to hundreds of thousands of years, and at a similar magnitude of around 10 centimeters to several meters. Those processes that vary in time also vary in space. So each of those processes has a spatial fingerprint on our planet. On the graphics here, we have ocean dynamics, which I just spoke about previously. Its magnitude can cause sea level change around our planet. This is from satellite-based imagery from 2000, from satellite and instrumental records of the 20th and 21st century, showing the potential change with a high emission future, looking at differences between around -3 millimeters to +3 millimeters. This is a process associated with land height, I'm going to explain in a minute, and this is a process associated with gravity. So this graphic here, this process is known as glacial isostatic adjustment. It causes deformation of the land surface associated with extinct or existing ice sheets. So if you are located underneath an ice sheet, the land subsides. When the ice sheet melts, the land uplifts. If you're located at the periphery of an ice sheet, when the ice sheet is at its maximum, you're elevated. When the ice sheet melts, that sinks. We can monitor that around the world using GPS information. So in areas in red are areas that were located at the margins of an ice sheet that existed 20,000 years ago called the Laurentide. And the Earth's relaxation to these loads is very, very slow. So still today, an ice sheet that it was its maximum extent 20,000 years ago and was extinct by around 7,000 years ago, is still causing land subsidence along the Atlantic coast and the Pacific coast of North America of up to 2 millimeters per year. Where in areas that were underneath the ice sheet, such as Hudson Bay, or areas of Scandinavia, are uplifting at greater than 3 millimeters per year. And this process is a dominant control on sea levels of the past and the present, and a significant factor if you want to understand sea level into the future. That last process, I'm sure you can sort of understand that if you have a colossal ice sheet in weight, the Earth isn't a brittle plastic, it will deform. This next process is rather counterintuitive regarding sea level rise, and it involves the change in gravitational attraction between these large masses of these ice sheets and the oceans. So when the ice sheets are at their maximum, water is attracted to it. When the ice sheet loses mass, the water retreats from these ice sheets because it's lost gravitational potential. So these are one of the implications when we think about the future. So on the top diagram here shows the modeling that we have done, showing, well, what's the spatial fingerprint if Greenland loses 1 meter of sea level equivalent? So Greenland melts and puts 1 meter into global average sea level. Well, counterintuitively, the coastlines around the Arctic Circle will see a sea level fall. And I always find that that's quite strange to think about. If Greenland was the only contribution to sea level in the 21st century, the Arctic coastlines would see sea level fall. The maximum impact of it in the dark red are the Southern Ocean and the tropics. So here in Singapore, if Greenland contributed 1 meter, Singapore would receive around 1.2 meters. On the bottom diagram is the opposite. What happens if we have a 1 meter contribution from the fastest warming place on our planet, the Western Antarctic Peninsula? Well, around the peninsula, you would have sea level fall. Along the coastlines of South America, you'd have a latitudinal gradient. And the hot spots are in the Northern Ocean and again in the tropics. A 1 meter contribution from Western Antarctica causes around a 1.25 centimeter rise in Singapore, or 25% of the global average. So when you're projecting the future, we have to understand which ice sheets are going to contribute, how much, where their sources are, and then map it spatially around our planet. So I hope you can now start to see how complex it is to understand future sea level rise. Okay, so to understand the future, you need to have an understanding of the present and the past. You need to be able to look at past climate variability and compare them with instrumental records or geological proxies. So this diagram shows the sort of like the sources of sea level information and their age range. So satellites take us back to around 1992, tide gauges just over to 100 years, and then we have to use a variety of geological or archaeological indicators. So archaeological, corals, coastal wetlands, sedimentary features, coral reefs, geomorphics. They can take you back hundreds of thousands of years, but we can look at the error associated with them. So when you're using instrumental, small error, but as you go back through time, you're increasing your error. So there's only so much information you can get out of that data. So let's look at sea levels of the past and some of the problems and how we're at the Earth Observatory trying to solve this. So we're going to look at the Holocene. So the Holocene is the last 11 or so thousand years. It's called an interglacial. The Earth goes through between glacial and interglacial phases associated with the orbit of the Earth around the sun, which changes solar radiation and the amount of carbon dioxide in the atmosphere, which produces the greenhouse gas effect. So the Holocene has the most abundantly and highly resolved relative sea level data. We have data from all around the globe. Particularly well, we can constrain what's happening with our ice sheets. We have but we still have a big problem in that we don't have a true understanding of what Holocene sea level is. So these are just 4 different publications that look at how sea level has changed through the past in terms of what the global mean sea level is. And I wanted to try and illustrate to you that the Earth has experienced in the past dramatic changes in sea level because ice sheets wax and wane. So 12,000 years ago, sea level was somewhere between 60 and 50 meters below present. And that means here in Singapore, if you were living in Singapore 12,000 years ago, you could walk to Sumatra, you could walk to Borneo. Singapore sits on top of a very shallow continental shelf that was exposed 12,000 years ago. Sea level rose, broke a lot of land bridges, and you get the island archipelago that you find in Southeast Asia. So what have we been doing here at the Earth Observatory of Singapore? One of the things that I've done ever since my PhD is I've tried to standardize geological measurements. And if you can standardize them, then you can compare a past sea level record from Singapore to a past sea level record from Stockholm in Sweden, or a past sea level record from New York City in the United States. So on this graphic here shows databases that we have published on past sea levels in the red, and 3 dashed ones are the ones that we're currently working on, which are closer to home to Southeast Asia. So how do we reconstruct sea level? So this is what I've been trained in my whole career. So how do you reconstruct sea level? Well, you use the modern information of your coastal environment to interpret the past. So this is a schematic of an intertidal zone. So it has what we would call 4 sea level indicators. So it has an upland, a freshwater community, 2 different types of salt marsh, high marsh and low marsh, and then a subtidal community. And quite simply, although we'll use a variety of different, more technical aspects, we can survey the upper and lower elevational limits of any one of these sea level indicators to define where it lives with respect to the tidal frame. So a low marsh, for example, we would find anywhere hypothetically between mean high water and mean tide level. Then in the fossil counterpart, we then take cores out of the ground, look at outcrops or riverbanks, and we take those cores, we survey them into a tidal datum, and then we extract datable remains that we know the time period of, and we try to identify if that's upland, high marsh, low marsh, tidal, flat. This is what its schematic shows. And then we can just reconstruct sea level by knowing the elevation of the sample, and from the previous slide, what their indicative meaning is. So to provide you an example, let's look at Singapore. So in Singapore, we've been taking a series of cores in and around the coastline of Singapore. And I'm going to show you one example here. It's from a new publication of one of my graduate students, Stefan, from Marina Bay. We took a core that went down in depth of around 19 meters. This is a core segment we're showing here, but in actual fact, we went it back around 40 meters, which took us back around 200,000 years of Singapore's Earth's history. But the top 19 or so meters looks at the Holocene, the last 10,000 years. The stratigraphy, what it's made out of, it has a sandy substrate at the top, sort of an intertidal mod, which overlays a mangrove environment. So 9,000 years ago in Marina Bay South, there was a mangrove existing. We can extract datable woody remains, which you can date through radiocarbon dating. And then we look at the microfossils. Here we're looking at the pollen to prove that it was a mangrove environment. We then can produce a sea level history for the Holocene for Singapore. So on these graphics, you're going from 0 back to 10,000 years. This is relative sea level. We've got a variety of different dating, but if you just look at the purple squares, it shows that sea level rose rapidly from around 17 meters below present to around 8,500 years ago, rose rapidly to sea level being above present. So Singapore, at around 6,000 years ago, had sea level higher than it is today. And that was all associated with Earth's surface processes. And then sea level subsequently fell, although we have large data gaps. Our work certainly isn't complete, but we can assume that sea level fell, as we've applied a statistical model, fell from around 5,000 years ago through to present. This text, it's relating to the models that can project back through time, and we can see significant misfits here in Singapore between a model that projects sea level back through time and our observational data. So regarding our models that project the future, we need to correct them based upon this data. Okay, so then what can you use data of the past to use for? So you can produce a graph and you can compare it with climate models. But one of the things that I was very interested in was trying to use data from the past to show how mangroves are very, very important ecosystems. So mangroves are incredibly important because they protect our coastlines, they filter our drinking water, they're a breeding ground for fish, and are incredibly important for carbon storage and capture. Mangroves are more efficient than any other natural solution for climate change. Mangroves in Singapore, although they're very, very few, each year they absorb as much carbon as 450,000 Singaporeans produce. So when you drive around the coastlines of Singapore, you may occasionally at Pulau Ubin, Sungai Buloh, would see some mangroves. And you say, well, what importance are they? And you can say, oh, yes, biodiversity. You may not know that they protect our coastline from storms, but you certainly wouldn't know that these very small ephemeral mangroves store enough carbon each individual year as 450,000 residents. So understanding the survival of mangroves, not only in Singapore, throughout Southeast Asia, is really, really important. So I wrote a paper in Science, our team wrote a paper in Science this summer, trying to look at the the geological data, and whether there was a tipping point. In the past, were there rates of sea level rise that caused the disintegration of our mangroves? Why this is important is because the modeling or observational data produces very contrasting results. So you can look at observational data using satellite-based imagery and instruments that can show, well, 69% of our mangroves are currently being lost. But then another paper can come out that, well, it's actually less than 5%. And then you can have another paper which actually shows that the mangroves are expanding. When you have bad data, models have a problem. So you have models different papers that have projected the future that have said up to 90% of them will disappear by 2100, or ones that will say at least as little as 50%. So you get a huge contrast. So what we're doing with the geological data is that we're going into our stratigraphy, just like you saw in Singapore, and where you have a mangrove peat that above it has a mud. What I want to know was what was the rate of sea level rise that caused that stratigraphic change from a mangrove to a mud? Or conversely, if you find in a stratigraphic profile where you got a mud to a peat, what was the rate of sea level rise that lowered enough to allow mangroves to form? So instead of using instrumental data, which only lasts 100 or so years, can we use geological data that goes back 10,000 years with vastly changing rates of sea level rise to find the tipping points? So this graphic just shows our database that we used. We used a variety of different settings throughout the tropics, looking at areas that had very different sea level records. So in Australia has a sea level record that's similar to Singapore, fast rising from 10 to 6, being above present around 6,000 years ago and then falling. We have areas in the Caribbean fast rising to around 6, but sea level was not above present and then gradually rose. And then we can think about how the coastlines evolved. So as I said, we looked at a variety of different locations. These are locations where mangroves formed between around 10,000 and 6,500 years ago. So sea level was going up so rapidly, mangroves couldn't form. Then it slowed down enough and mangroves formed somewhere between around 10 and 6,500 years ago. In these sites, mangroves only formed around 6,500 years ago. We then did some analysis about how mangroves keep pace with sea level and compared the amount of mangrove accretion, that's how much sediment it can absorb to keep pace with sea level, with the rates of sea level rise. And we could see a very, very close relationship that whenever, as sea level slowed down, the ability of the mangroves to accrete slowed down. And this bottom graphic is the key one. Is this graphic here. So this graphic here shows rates of sea level rise along the x-axis and the probability of marsh submergence along the y-axis. So what we're looking at here is that the rates of sea level rise, when the rates of sea level rise are around 0.6 of a millimetre per year, you have around a 90% probability that the marshes will drown and become extinct. So we were able then to start to think about tipping points. So this is what this table tries to indicate, that when the rates of sea level rise globally are 6.1 millimetres or greater, we have around a 90% chance that sea level rise will cause the mangroves to drown. If we divide it into different areas, we think that in areas around Singapore, which are called true far field, it's around 7 millimetres per year. I wrote a paper looking at salt marshes, which are the temperate equivalent of mangroves. And in there, we also showed a similar number. We showed that at around 7.1 millimetres per year, there's a 90% or 9 times out of 10 that the mangroves will retreat. And then in this paper written by a colleague of mine, show that if rates exceed 6 to 9 millimetres per year, the marshes of the Mississippi Delta will also retreat. So there's some sort of convergence in the paleo data that says that when you approach 6 to 9 millimetres per year, these incredibly important coastal ecosystems will disappear. So if you remember that number, it becomes very apparent when we start to think about projections for the future. But first of all, let's look at the instrumental data. So instrumental data, Well, we have satellites. Satellites orbit the Earth and they provide information on sea surface heights in the open ocean. They're unable to provide sea surface heights around the coastlines because the bathymetry is too shallow. But in the open ocean, they provide incredibly accurate information about how sea level has been changing. But they've only been in existence since 1992. If you want to get instrumental measurements prior to 1992, you need to use tide gauges. Tide gauges were put in place by mariners to understand high and low tide. The average of high and low tide is the average sea level of that day. The average of those over a year is the average sea level of those years. And then you can have a time series that goes back through time. So on this graphic here, we show individual tide gauges at the bottom, and they all differ. And they all differ because of the processes that I've discussed to you previously. So New York City was at the margins of the large Laurentide ice sheet, so on that full bulge. So that has been collapsing. So in New York City, we get around a 40 centimeter rise in sea level. The global averages are shown here, and although they're on millimeters to centimeters, it's somewhere in the order of 15 to 20 centimeters. And New York City has twice that value because the land is subsiding. If we look at Marseille, quite like the global average, but has significant variability. San Francisco, significant variability related to El Nino cycles. But look at Stockholm in Sweden. Stockholm in Sweden, over the instrumental period of the last 100 years, doesn't experience sea level rise, shows a sea level fall of over 40 centimeters. And that's because 20,000 years ago, it was underneath the Fenno-Scandinavian ice sheet. So it has been uplifting from glacial isostatic uplift. So to understand what's happening globally is difficult because you've got all of these different tide gauges located throughout the globe. They all have different processes, and then there's an uneven distribution. Prior to the 1950s, the only long-term tide gauges were really found in North America and Northwestern Europe. So it's very difficult to calculate what global mean sea level is. But a variety of people have done it by taking different subsets of data and using different statistical solutions. And that's what this top diagram shows. Top diagram shows that irrespective of the subset of data or the statistical method used, that sea level has been rising in the 20th and 21st century, and indeed it has been accelerating, which can be clearly seen in this graphic I put together for that annual review. So I went through all of the data, and in this graphic, in the green is the 20th century average, and in the blue is the average from 1992 to 2018 or 2017 when I published the paper. So here's just looking at tide gauge data, and in the top is satellite-based measurements. And they have different values depending upon the study. So 20th century values can vary from nearly 2 millimeters per year to down to around 1 millimeter per year. And estimations from 1992 to 2017 can be anywhere from around 3 millimeters per year to 3.5 millimeters per year. And they've got an uncertainty associated with it. But irrespective of those values, you can see a significant difference between the 20th century and the latter 20th and the 21st century, showing a clear increase in rate. Okay, what about the future? So as I sort of started this presentation, I'm an earth scientist, so I haven't been involved in projecting future sea levels. But as I illustrated previously, I spent my whole career trying to standardize sea level. So what I thought about was the first thing I should do is try to standardize projections, because projections have changed. The first projection, as I'm about to show you, occurred in 1982. And then we've had an increasing number of projections as you go through time. So we published this paper. So this was by Andra Garner. She was a postdoc of mine a few years ago. And we looked at the evolution of sea level. So this graphic here shows a time series along the x-axis from 1982 to when we published the paper in 2018. The circles are the number of emission scenarios considered in each individual paper that projects sea level. And then the total projection is just the number of studies, okay? And so the first ever study of sea level was in 1982. So it was by a scientist, Vivian Gornitz. She works for NASA Goddard Space Laboratory, and she just did one projection where she just doubled CO2 and looked at how sea level had changed. We have a series of, there weren't many papers on sea level rise really until 2007 and beyond. We have less than a few papers per year. Indeed, between 2001 and 2007, there wasn't one single scientific publication on sea level, which I always find, considering there are so many by now. You know, in 2017, there was over 50 papers on sea level using 11 different projections. When I mean projections, they use low emission, high emission, Paris Agreement, what are called RCPs, which are representative concentration pathways, 2.5, 4.5, 8.0. So there's been a very uneven distribution. In the dotted lines are the IPCC projections. So the IPCC reviews the literature. So I would imagine the first assessment report that was reviewing the literature was quite happy, only had a few studies to deal with. The second with the second assessment, the third assessment. I think the fourth assessment, they did have problems because between the fourth assessment and the third assessment, there wasn't one published study. So how were they able to review the science if there were no published studies? So they did some science themselves. The fifth assessment then ran into problems because there were many different projections that would produce contrasting results. And now we're dealing in 2020 with numerous papers and numerous projections to do with the sixth assessment report. The other interesting thing is that the IPCC projections, I would say, are conservative against the individual studies. So what we're showing here, again, on the x-axis is time of when the publications were made. And we're looking at sea level projections out to 2100. And we're looking at the high emission future. So this looks at the time of publication, sea level rise out to 2100, and the timing of and at high emission future. So in the bars are the bars from the IPCC's report. So if we looked at the top bar, that's their upper assessment, their high-end sea level, the first assessment, the second assessment, the third assessment, the fourth assessment, and the fifth assessment. And I said, for example, in the fourth assessment, there were no studies to compare it to. But the interesting thing is if you go into those individual studies, their upper estimate are exclusively either equal to or higher than the IPCC. And I would assume that very few people outside sea level science know that the IPCC is a conservative body when it comes to projections of sea level. So if we look at the fifth assessment, it projects an upper estimate of around 98 centimetres, whereas individual studies, yes, they may hit 98 centimetres, but they can be greater than 2 metres. So this, when I got involved in the fifth assessment, this concerned me. So I wanted to go in for a little bit of a deeper dive on this. So I can't produce projections myself. I don't have those scientific capabilities. But so what I thought about, which is a very useful technique when there's deep uncertainty associated with any problem, is that I did a survey. So I identified the 100, what I would call top scientists in sea level science. So what we did is we ran a database search of the Web of Science to identify the 100 scientists who produced the most papers on the topic of sea level. We got a unique identifier for them, and then we sent them a survey to ask them what they thought sea level rise was. So we sent them a survey where we provided them with this information. This is the latest information on what temperature will do going out to 2100 and 2300 in the low emission in blue, which you could think is the Paris Agreement, and the high emission in red. So we asked them, what do you think sea level will be low and high emission at 2100 and low and high emission at 2300? And I did this survey both in 2014 after the 5th assessment report, and then I repeated it this year. So this is the graphic that was produced with the people responded, and then you were able to produce probability density functions to identify what are the lower and upper limits from these experts. And so I did this survey in 2014 and I did it in 2020. So if you just compare those, we've got, this is RCP 2.6, low emission, high emission. The top row is 2100, the bottom row is 2300. And we can see similarities between the curves. You could say that there's an evolution between 2014 and 2020, that we're more certain of what sea level will be at the low emissions. But particularly when we go out to 2300, we are more uncertain and particularly very, very worried, because certain respondents predict sea level rise by 2300 to be well in excess of 3, 5, and even 10 meters. So certain experts predict the collapse of the Antarctic ice sheet, because that's where the source of this water is from. So if we try and summarize that, so in 2004, if we just look at 2100 and then we compare them with the IPCC. So if we look at the high emission scenario, so this was a survey I ran in 2014, and this is the survey I ran in 2020. And it compares it with the ranges from the 5th assessment and then IPCC's special report from 2019. It's called, references IPCC 2019, but it's also called the Schrock report. And we can see that the scientific community for 2100 is predicting an upper estimate of around at one standard deviation at around the 83rd percentile of around 1.4 meters, and at 2 standard deviations we're predicting around 1.6 meters, whereas the IPCC is just under a meter or just over a meter. So I think that again is something very interesting to think about, is that the models used by the IPCC are under-predicting compared to other sources. We can skip this slide, but this slide is just like, I was interested in asking the experts where they got their information from. What was, if an expert's saying, right, I'm thinking about sea level, where are they getting their information from? What's quite interesting is that they get their information, the vast majority of them, from this study of DeConto and Pollard. DeConto and Pollard's paper was published in 2016 in Nature, and it was a paper that predicted the collapse of the Antarctic ice sheet at the latter part of this century, and therefore continuing through the 22nd and the 23rd. The experts preferred the information from this than the IPCC itself. So let's try and pull all this together. Okay, and so if we try and summarize this, sea levels in the past. So we've got 3 locations here. So I've got an animation running in the top, which shows these big ice sheets changing in time from 20,000 years ago through down to present. Big ice sheets, the Laurentide and the Fennoscandinavia. You can see how they rapidly shrink in the Holocene between around 10 and 8,000 years ago. How does that influence sea level in the past? Well, in areas in Scotland that were underneath the ice sheet, where I did some of my PhD work, sea level rapidly fell because the land was underneath the ice sheet and it shot up over the last 6,000 years ago. New York City, where I worked prior to coming to Singapore for 15 years, we produced our record in New York City. So this was at the margins of the Laurentine ice sheet, so uplifted at the last glacial maximum and has been sinking. So sea level has been rapidly rising over the last 10,000 years. What about closer to home? We've shown the Singapore record. Manila is exactly the same. It rises, sea level slightly above present, around 6,000 years, and then falls through to present. What about the instrumental record? We've got a different subset here, which I'll use to provide as a context for the projections. So Stockholm in Sweden, we've already discussed this. Over the last 100 years, the land has been uplifting because of that ice sheet, causing sea level to fall some 50 centimeters in the last 110 years. New York City, sinking. It's been sinking, and therefore sea level rises around 50 centimeters in the last 150 years. Global average is around 15 to 20 centimeters. Manila, slowly rising, but then this sharp increase in the 1970s associated with groundwater withdrawals, currently doing around 15 millimeters, 1.5 centimeters per year. So let's look at some projections. So these are projections from a paper by Bob Kopp, who's been one of my colleagues for the last several years. And it uses the DeConto and Pollard ice sheet model. So what are our projections into the future? So we're going to look at comparing Stockholm with New York City. So Stockholm, so we're going to look at emission scenarios. In red is the high emission, in blue is the low emission. If we compare the two areas, so Stockholm in Sweden under a low emission future, because the land is uplifting faster than the oceans, they won't have a problem of sea level rise. They will have, on a 50th percentile, sea level fall. If you get a high emission future, you can see the stark difference you've got from sea level fall to sea level rise. For the first time in 20,000 years, Stockholm will experience sea level rise if you're on a high emission future. What the impacts there are of geomorphology, of engineering, of coastal populations that have had a stable coastline for 20,000 years and it changes, I don't think any geomorphologist knows the answer to that. In New York City, we've had subsidence. So over the next 50 years, and it's interesting to look at both of those, it doesn't matter on emission scenario, low or high emission doesn't matter for the next 30 years to 2050. Very much driven by local processes. As a high emission of around 40 centimeters, Stockholm is 1 centimeter. When you draw out to 2,100, sea level rise at the 50th percentile for New York City is 1.7 meters. What about in Singapore? So in Singapore, let's look at a low and high emission future. So if we run out to 50 centimeters, it's obviously higher than Stockholm because it doesn't have land uplift, but it's less than New York City because it doesn't have land subsidence. There is no difference between the emission scenario, about 28 to 20 centimeters. But as you run out to 2,100, because this model uses a disintegration of the Antarctic ice sheet, the difference is profound. 51 centimeters. Currently, if you looked at the tide gauges at Marina Bay, they're doing around 4 millimeters per year. If you go out to 51 centimeters, the rate of change is up to around 6 millimeters per year. Remember that threshold for mangroves? 7 millimeters per year. That means your mangroves, your coastal wetlands will survive. Under the high emission, when you get out to around 2050, the rates top 7 millimeters. When they go out to around 2080, they're doing 20 to 30 millimeters. By 2100, they're doing nearly 40 millimeters. The Earth hasn't seen 40 millimeters of sea level rise for 14,000 years. All your coastal ecosystems become extinct. And there isn't an engineering solution that can be built fast enough to stop that. Sea level rise, if you guys knew what I knew from 25 years of studying how the Earth responds to sea level, It's an existential crisis to the planet. We live along the coastline, our infrastructure's on our coastline, and our most important carbon storage is on our coastline. They will all go if you don't tackle climate change. And that, going all the way to back to the beginning, is why Biden has to win. He has to win. I don't care about anything else that he campaigns on, but climate change is his key element. And if it isn't bad enough for Singapore, what about Manila? Manila's got this groundwater problem. Manila has a problem that by 2050, it's got the same rate of sea level rise that New York City has by 2100. And look at those values, 2 meters. And that's the 50th percentile. Look at the 95th percentile, the 1 in 20 chance, 3.2 meters. So I hope in your course that when you're considering climate change, that you understand how urgent it is. Prime Minister of Singapore said that after we recover from COVID pandemic, we need to be ready for virus X. Virus X is climate change, and we haven't got a vaccine for climate change. You know, if you melt an ice sheet, if we melt the ice sheet in the next 50 years, it takes 100,000 years to regrow it. There's no engineering solution for that. That's my important message, guys. Okay.
Thank you so much, Professor Horton. I think that was really a very important message and a very wake-up call for those who had not realized the extent of the problem. I mean, yesterday with Professor Voigt, we were discussing how this is the critical decade where this is the time to act now. And I think that the UN also has been quite united on that. Of course, it's very interesting from your presentation to see, on the one hand, how science is made and how it is consolidated and how it has become in academia so evident that this is a real problem. The issue is now this passing on to the political level and for political actors. I don't know, maybe if I can just go, there are 2 questions in the chat. I will just ask them very quickly. And one of them was about, is from Marcus from Singapore, about mangroves, whether they're more effective at carbon capture than other types of flora. And the other question is from Winston, also from Singapore. And it's, if I can simplify it, it's really about whether we have passed or not the tipping point, especially based on the NASA estimates regarding the emissions and the rise in global temperature. So perhaps you could just quickly comment on that. I know you're pressed for time, but on the question of mangroves and whether we've passed or not the tipping point.
Well, I mean, the idea of mangroves is so a lot of people ask questions about, you know, carbon capture technologies. So you know, I try to show you some of the science behind it, but people always want solutions. So they want to know what the answers are. So people will say, well, what about carbon capture? Can you know, carbon dioxide has been the blanket that has basically preserved life on our planet. If you didn't have carbon dioxide in the atmosphere, we'd be too cold for life to exist. So we need carbon dioxide. And the Earth has always been producing carbon dioxide through the biosphere, through volcanic eruptions from the oceans. So we've had a carbon cycle that recycles it. So the simplest answer is to try and, I don't know, catalyze the carbon cycle, to try and use what Mother Nature has provided. And the most simple thing is through the photosynthetic equation. So you know the photosynthetic equation, you have light, you have carbon dioxide, it produces energy and it produces oxygen. And the carbon is stored within roots and plant material. And mangroves are one of the most efficient. It has about 3 to 5 times the storage capacity of any other forest type. So when we think about climate change in the 20th century, about when you look at we look at sort of like the radiation budget of the Earth, it's increased 2/3 of it to do with putting greenhouse gases in the atmosphere, but about a third of it is land use change. We have deforested our planet. So if we want to try and answer your second question, if you want to try and stop us passing this tipping point, we have to stop our deforestation of our tropical rainforests. They're very close to a tipping point, and also our mangroves. I mean, we have a unique opportunity right now because, obviously the COVID pandemic has been terrible. My daughter got COVID back in the US. It is not flu. I saw my daughter. She's okay now, but I saw her suffering from it. It is a horrible, horrible disease. But a legacy for the people who've lost their lives, lost their income, is that we have a unique opportunity to reset our economy as we come out of it. The European Union has signed up to this. 40% of their money that they're putting into the European Union has to be related to a green technology. And then you can stop it. You have to try and... The Paris Agreement is the key for hope. The countries came together in 2015 and produced a roadmap to stop us passing the tipping point. The tipping point in sea level is around 2 degrees C greater than the global temperatures at around 1880 prior to the Industrial Revolution. We're already around 1 degree C. We've only got a wiggle room of 1 degree C more. So that's why it's all this. By 2030, we need to peak our energy costs, and by 2050, become carbon neutral. That science went into policy, but it needs to be acted upon. And it's down to consumers, it's down to the public to force their governmental officials to look after yourselves. I talked about my daughter. I have 2 boys, and I'm very, very worried about their future. My mum and dad didn't need to worry about me. They didn't need to worry about climate influencing my son's livelihood. That didn't enter. But for all of you on here, it's going to be a big problem. You have to get involved on climate change. Make your right consumer choices. Only buy things that are environmentally friendly. Talk to your colleagues. Talk. I've always thought about climate change. The big thing is education. If you know the facts, you're more likely to act upon it. If you're forced to do something, a lot of people will rebel. And so it's all about education, So if there's one thing you guys could do for me, is that where at some point this evening you have a climate change conversation with your friends, your family. Talk to them about what you know or what they know and have a conversation, And if I was talking to a group of Americans, I know what I'd say. You vote Biden.
Thank you so much. I see now that there's a few more questions, but I really understand that you have another commitment.
I can keep going for another 10 minutes.
Okay. Yeah. So I will ask then one of the questions also from Angus from Singapore. I think it's quite interesting what you said about the IPCC being conservative in its approach. And the question is why wouldn't it be more compatible with the precautionary approach for the IPCC to take a more dire approach instead? And perhaps you could answer that.
Well, the first thing is it's a review. Okay, so it will review the science, and also it is scientists generally are conservative. If you have an upper estimate and you're below it, you won't be discredited. If you go beyond it and are shown to be in error, you're discredited. I mean, it's just a natural thing. There are individual scientists that will put their neck on the block about it. So the most famous one is James Hansen of NASA, who was the first person really to talk about climate change in the 1980s. And he was the one who went to Senate to say that we have a climate emergency. Al Gore is another one, a politician who wrote The Inconvenient Truth. I mean, you have individuals who promote this, but the IPCC as an organization reviews science. And then there are some limitations. So the IPCC, so if we think about the IPCC in the fifth assessment report, what they have to do is they have to produce a value and then a confidence level associated with it. And so they had low confidence in some of these higher values, and that's why they downgraded it. Okay. The IPCC also don't include the full ranges. So one of the things in the fifth assessment report, they said sea level is so uncertain that I can only look at a likely range. And that means that I'm only have a high confidence in understanding sea level between the 17th and the 83rd percentile. So if we're looking at the upper values, it said anything from the 83rd percentile onwards, I have no confidence in that because we don't understand the processes. An individual person or modeling group doesn't have those constraints. It can go and project to the high end. In the IPCC right now, we've had weeks of conversation trying to decide on what the upper value is for global average. And we still haven't got that number. And we've been working on this for weeks. And that's a team of about 20 people who've been studying sea level all their life, and we cannot come up with a number yet. We're arguing about whether it's 1.4, 1.5, or even 2 meters. What is the high end? Because we want to do it this time. The IPCC reports previously shied away from it. We want to do what the questioner asked. Why can't we produce a high end? We're trying to do it, but we can't come out with a value right now.
Okay, thank you so much. You think you have time for one more question?
Maybe I should acknowledge the person who appreciated the picture of Alex Ferguson behind me. So I'm from Manchester, okay? So I'm a Manchester United fan.
Very good. I guessed that when I saw the photo. You want to choose any of the questions, or we also have a participant asking for the floor for a live question?
What question is that?
From Giacomo. From Germany. Should we allow a live question for change?
Sure. Yes, question.
Giacomo, you have the floor.
Thank you so much for this opportunity. Professor Horton, your lecture was incredibly interesting. For example, I never heard about the glacial isostatic adjustment, which was quite a new thing for me because I'm not a natural scientist, I'm a jurist. But what I'm wondering about now, after all the insights you gave us, in how far is the knowledge, especially you gained through your research, somehow being caught up with in politics or in governmental bodies that have a scientific approach? Maybe in different world regions, you say you worked in the US, now you're working in Singapore. And how far is there awareness about these rather complex systems that produce everything concerning sea level rises? And the second approach, given the fact that those things are so complex, what is, let's say, your personal approach to communicate these findings, to educate people in your closer, but also in your farther social field? Because those are things, for example, I mostly never heard of. And it struck me that it took me this lecture, which is also for a very limited number of participants, to find out about this. What is your approach for that problem?
Okay, so they're two excellent questions, okay? And I have an answer, and not particularly. The first one, it's a problem. Communicating science is a problem, and it gets lost in translation to the people who actually matter. So I'll give you an example of this. So the Singapore Land Authority, which basically provides the information for all building projects here in Singapore, they estimate that sea level will not be greater than 1 meter by 2100. So everything in Singapore is planned for a 1 meter sea level rise. When I first came to Singapore, I had a meeting with all the agencies, and they were saying, so this is NEA, SLA, PUB, all these different acronyms of all these agencies that I didn't have a clue what they actually meant, but eventually I did. And I got this value of 1 meter, and I said, well, where do you get that from? He said, oh, well, we got it from NEA. And then you go to NEA, where did you get it from? I said, oh, well, we got it from the Hadley Centre in the UK. And then you go to the Hadleys. Well, how did you get to 1 meter? And then you find out that 1 meter is the 83rd percentile of the global average. That's what they used. They used the IPCC report in 2014, which had 98 centimetres. That then was given to NEA with a big, large report talking about this is the 83rd percentile at the high percent. We're not including the upper end. It's just the 83rd percentile. But all the other agencies just think that's the upper end. And then I tell them, well, that's the global average. Singapore's greater than the global average because of gravitational effects of the larger ice sheets. And it's only the 83rd percentile. You've got, and then they're like, oh my God, we're under planning for sea level rise. So that's one problem, okay? So the only way to overcome that is to try to educate through presentations, but most importantly, get the agencies that make the policy decisions involved. So that's a big thing that we do at the Earth Observatory. We try and second people from the agencies to work alongside us. I think the big thing is education. That's the real drive on this, that everyone. So you said that most people won't have heard of glacial isostatic adjustment, but what I'd ask you is, how many courses did you ever take on how the Earth works or climate change? So when I was in the US, I worked at the University of Pennsylvania. So University of Pennsylvania's got Wharton there, the business school that everyone goes to. Christ, Trump went to it. Okay, so what I was thinking about was that I wanted to educate everybody at Wharton Business School on climate change. So I approached them and said, well, can I run a course for them? And they went, yes. So everybody, when I was at UPenn, everybody in that business school had to take a course on climate if they were doing like a specialization on risk. And so we got, 40 people every year, movers and shakers. I keep on talking about Trump, but I had Tiffany Trump, his daughter, took my class. She aced it, which is quite interesting on climate change. Here at NTU, what we're starting at NTU is that every single student, doesn't matter whether they're medics, law, social sciences, the arts, will take a course on sustainability. Every single graduate of NTU will have to pass a course on sustainability. That's the future. And people will know how the Earth works. That's what I think, anyhow,
Thank you so much, Professor Horton. I think that point that you make about mainstreaming science, and in particular about climate change from all the areas of activity, from economics, law, and politics, it's really a key point. And that's why we really wanted to have you so that we can also know better what's the science when we think about the legal solution. So thank you again so much on behalf of all the participants, on behalf of the Academy, in particular Nilofer and myself, especially for running overtime and staying with us a bit longer and taking up so many of the questions from our participants. Thank you so much once again. All the best, and to our participants, see you tomorrow.